continuing on with chapter 2, we now add another dimension to our system. So here's an example where we have a third dimension. And this other dimension, or the axis for the other dimension, which is perpendicular to the plane made by the dimensions with the coordinate system we already dealt with, the x and y plane, we now have a new dimension or a new axis off that's perpendicular to that plane. Okay, this is where you define, the author defines Cartesian vectors. And what we're going to start with is this idea of a unit vector. Okay, and one of the things, the main point of a unit vector is going to give us direction, right? Okay, and thus far we looked at these unit vectors, the I and j unit vectors. I being for telling us that we're in the direction of the x-axis, and j telling us that we're in the direction of the y-axis. Okay. Some things to pay attention to, of course, is the magnitude of the unit vector is 1. And it has no dimensions, and it points in the same direction as a vector, right? So you have, like in this case, UA is the unit vector of vector A. Could be anything, right? Could be any direction. And here's its magnitude. So here's like the original vector and the magnitude of that vector, right? And what you recognize that if you did like the, the magnitude of this, or using the distance formula, let's say, or Pythagorean theorem, this magnitude, of course, would come up to be 1, right? Okay, so as before we had I and j, now we have k. All right, so let's say we have a vector A. What we can do is break up that vector into its individual components in each of the directions with magnitudes associated with it. So this basically identifies what's the magnitude along, or how far along, this one, the x-axis. This one is how far along the y-axis, and this gives you the magnitude along the z-axis. Okay. And then, of course, as in the past, when we had a 2D vector and we wanted to find the magnitude of the vector, we could just, square the individual components, or the magnitudes of the individual components, and get the square of that, and we have that magnitude. Okay. And one of the other things is how we look at these. So what you can consider is that you can come up with the magnitude of this, or sorry, the square of the magnitude of this component of my new vector A prime, and then you can use that, or let's say that that's going to be equivalent to if you had the individual components by themselves. And we use that in some of the examples, and you'll see is how the examples are defined is that writing it or solving it in like a two-step fashion is simpler, or more appropriate for the actual problem, how the problem's worded. Okay, so here's another example. And this is where we start to look at this idea of like a direction cosine. Okay, so with direction cosines, really, if you think about breaking up this, vector, or looking at it from the perspective of having a plane, let's say this blue line is A, in each of the axes. Okay, so if you made a plane with just like x, the x-axis, and the A vector, you could actually have an angle like between these two vectors, and the angle between those two vectors would be identified as alpha. So you're just kind of taking it and looking at it from the perspective of being 2 dimensions, right? So you're taking this 3-dimensional one, and we're looking at it from the perspective of 3 essential 2-dimensional vector problems, okay? So just for example, like I said, here's alpha, and here's a plane made by vector A and x. And we could do the same thing for the other two, right? For beta. We make a plane for y, and um, where our a vector and y lives on the same plane. And then we do the same thing for z. Here's the z one. Okay. So it's just a different way essentially to represent the same thing. Okay. And as before, when we had our vectors I, j, our unit vectors I, j, and k, we can use that to represent um, a vector. And we can also do it with the direction cosines. Okay. So just if you make that substitution, what you'll see is that, ax over a is just cosine of alpha, which was defined here, and ay over a is cosine of beta, and az over a is cosine of gamma. So um, so all we're doing essentially is applying, the trig function cosine trig function in like three individual two-dimensional problems, right? Okay, that's it. So that's the main point here. Now, of course, as before, if we wanted to come up with a resultant vector from these, we would just add the individual components like before, except now you have this additional direction along the z-axis. So what we'll see is in these problems, you're going to have coordinate direction angles, which will have magnitude and coordinate direction angles, or we also will see problems with magnitude and projection angles, meaning the angles along a certain plane, where that will be given. Okay, so we'll take a look at an example and see that. Okay, so in the end, it really doesn't matter, either form. You can, however you're given a problem, when you come up with an end result, or even representing the vector, you can always go to this form, okay, Cartesian form. Okay, so here's an example. And one of the things you'll notice in this particular case is that the information is given like as a projection, the angle projected along some axis, okay? And we have like, if one of the things you'll look at when we look at these problems is you'll see that you have like another vector here along this line. So we have created like this intermediate vector in the xy plane, okay? And we'll use that information, all right, to solve this problem. But it could be that, and sometimes it's hard to visualize these 3D problems, but it could be that the information is given in this fashion, okay? What you recognize here is that 30 degrees is between the x-axis and the vector here. That is, like I said, an intermediate vector that's in the xy plane, okay? Then the 45 degrees is basically an angle between that vector and this intermediate vector from here to here, essentially. Between that and the vector made by this rope, okay? And this particular problem, this is just between the this point here or whatever. There looks like a meeting at the meeting at the origin here. This is along this cable is along the y plane. Okay. Okay. So here's just a plan. So in this case, you have two vectors. You can write the two vectors in Cartesian form and then add them together. Okay. So not only two main steps. So if we just take a quick look at that. So we take a step back and we look at one of the ways that the vectors are represented, right? So I'm just going to quickly step back and show you where this comes from. We originally defined. Okay, so right here. That's all essentially what we're doing, right? We're representing the individual like unit vector components in that fashion and multiplying them times the magnitude. Okay, so going forward again. Okay, here we go. Okay, another term they use is this idea of like similar triangles. So you also can come up with a relationship. This is, if you think about it, this is kind of like our either our you know, cosine function or sine function relating the two sides, right? So we can think about this as like just our trig functions. This is the cosine of the angle, which essentially just means here's our adjacent side and our hypotenuse from this triangle, and here's like the opposite side in the hypotenuse, up divided by the hypotenuse. Okay, so you can rewrite this first vector. Oh, sorry. Rewrite the first vector from this. Okay, here's our magnitudes, the force magnitudes here of the individual components. Okay, then the second one vector is a little bit different. Like I said, you have this intermediate vector that you create, so you make like a two-dimensional problem. Um, so first part of this is the z component. You can get that directly. You can get the z component, and the way we do that is think about it in terms of like you have this other vector, like I said, f2 prime, and this is basically making the problem a 2D problem, right? Relative, where you have a plane made by this vector and the vector f2. Okay, so if you think about it in that terms, you can actually just find the z component here. Okay, and that's all they're doing here. So they break it up into two components, break it up into a z component and another component f2 prime that's essentially along this axis. So if you think about it, it's really analogous to what we had seen before, where you have like this could be our x component and this could be our y component, right? And then it's just a two-dimensional problem, right? So we're basically seeing how much of this vector is projected along this, our intermediate vector, let's say, and how much is projected along our vector in the z direction here, okay? So by doing this step, essentially you're coming up with a component, our z component. So this is our z component, and then an intermediate one, let's say, like how much is projected along this vector here, okay? So now I already have the z component, so now I need to break this one up into how much of this vector is along the x and how much is along the y, okay? So we follow the same process before. We're given an angle. We want to find out how much is over here, essentially, and how much of that vector is along here, okay, or the length from here to here, right? We do that. We're going to use the same thing. We're going to use the trig functions to perform that, just like before. We look for the cosine to give us the adjacent side, which essentially is this or this, same thing. And then the opposite side, which is this. Okay. So now you have the components. So here's my z component, here's my x component, here's my y component. Okay. So you just write that down into a component form, and then you can go and just add the individual components together. Okay. So here's another one. In this case, information is given a little bit differently, but it's the same idea. And really, that one of the main points is to follow along and make sure you do it step by step. Okay. So we could follow the same plan as previously, and note we recognize we have this like intermediate vector here. Okay. All right. So this one is actually asking for the angle. So it's like you have an additional step. Okay, so the actual angles between that vector or the resultant vector and each of the axes. All right, so here's our f prime like previously. Follow the same process, come up with a z component. Here's the this f prime vector or component along the amount of it that's along this axis, right? Because it's the same thing as before. Here's our 2D plane. Then taking f prime and breaking that down into its components. And we can just write down the vector f1 in terms of its components. Okay, now f2. F2 in this case, it's right along the ZY plane. Um, oh, I'm sorry. It is not along the ZY plane. Forgot about this right here. So we have 120 degrees here, right? So this one actually has, if you look at it, how it's written, it's actually uses the direction cosines. Okay. So we have its magnitude and we have the angles. Here's the direction cosine. Here's my alpha. Here's my beta and gamma. Okay. So it's a matter of just solving it using the direction cosines or breaking it up into its components using the direction cosines. Okay. So here's now F2. We have the components. Then all we have to do is go through to come up with the resultant is add the individual components, okay, to come up with the resultant. So it's pretty straightforward. Just add these two together, add these two together, and add these two together, okay. And that gives us our resultant vector. Very easy to find our magnitude of that with Pythagorean theorem. And then we can find the individual components, okay, because we have the x, y's, and z's for that vector. So it's pretty straightforward. All right. Okay, continuing on. What I failed to mention, the previous one also included section 2.6. Okay, so it was 2.5 and 2.6. So now we have section 2.7. This is position vectors. So we also, what we can use is, we can also use vectors to represent like a location or a position of something, okay? So before we used it in terms of, we used it for forces, we used vectors for forces. Now we can use vectors to, or we can also use, I should say, we can also use vectors to represent a position. So like for this example, we have a vector r that represents essentially position. So we can actually find like the length from A to B, okay? So in this case, maybe you'd set this as being the origin, and you have multiple, cables, or and you want to have a vector represent this cable or, position of B relative to A, okay? Here's another example. And one of the important points we're going to notice, and when we do this, is that when we're dealing with cables or, thin members where we're connecting 2 points, is that the directions are the same, right? So the direction of this cable is essentially the same as the direction of this vector, our force vector, right? So, let's say if this is my origin, this point relative, or this point relative to this point, if this was A and this is like B, so B relative to A, what we would find is that, in terms of direction of that vector, it's going to be the same as our force vector, okay? Which will be important when we solve problems like that. Okay. Here's another one, three-dimensional case. So you have some, cables holding up an awning, and it's the same idea, right? You can use that. So we could actually come up with maybe like a virtual connection point where all these cables come and meet at some point, and we can use that to go and solve like this problem, right? You could find out like how much force is in each of these cables and their directions too, okay? Why do we want to know these things? Well, we want to make sure that this can hold the weight, right? With snow and anything else potentially on this, or the wind or some other forces, make sure this doesn't collapse, right? Okay, so here's our position vector. Same idea as before. And we have like another point to pay attention to this, or another concept here. Let me see. So you really have to start off with some origin and, some coordinate system, and we're going to use our X, Y, and Z, or the Cartesian coordinate system. But let's say that you have A and B in 3D space, okay? And then you have the coordinates, the lengths of these XA and XB. Here's the magnitudes, right? These are the magnitudes of our vectors. So you're starting off with, let's say, starting from here, you go to point A, okay, that's a vector, and then you have another one from the origin to point B, okay? And you represent it with the magnitudes. Here's essentially the magnitudes of each of the X, Y, and Z's, okay? And all this is saying that if you wanted to determine this vector, right, from here to here, you can think about it in a couple different ways, right? You could say, let's say I'm from here to here, and then go from another vector from A to B. That's the same thing as saying going from this point to B, right? So what we could do is say that like a vector from here to here is essentially equal to this vector from here to here, which would be A, and then from A to B, and add those two together, and you got this vector. Or if you take and put it on the other side of the equation, essentially it's going to be just, you know, R A to B is essentially just the vector or the components of that vector, B minus A. Okay. So here we go. So this is how you would write it. RA to B is essentially just starting off with saying we have a vector, you know, RA plus RAB gives us RB, or like I said, you move it to the other side of the equation, then you're just essentially subtracting out the A component, right? So RA, or a vector, yeah, R subscript A, let's say, going from here to here, plus this one equals this. So if you subtract out this vector from the other side of the equation, this is essentially what you have in terms of components, okay? Just a note, always subtract tail coordinates from the tip coordinates, okay? Got it. Okay, so 2.8, think about a force vector directed along a line. All right, so here's an example. Okay, so we have some, some force acting at this point from A to B, okay? And let's say, now, one of the things we pay attention, thinking about here is it's a little bit different than what we looked previously, because typically we had a vector or force vector was relative to the origin. Now you have another vector that's relative to a point somewhere else. Okay, like here is A. So we have this vector RAB. So we've created this new vector essentially from point A to B. Okay, and we can represent that just like before, right? We have some unit vector from UAV, right? This is just, here is the vector itself, and here's the magnitude of the vector, and you can come up with a unit vector. Okay, and then of course we can come up with, anytime we have a vector, we can always represent it as direction times its magnitude. Okay, all right, so here's an example. We have a couple of cables here pulling down on a pole. Okay, and what we're going to do is we want to find the force vector from A, in vector form from A to C. Okay, so if we see that in this case, you know, from A to C here, this is what we're looking for. We have some magnitude, which we're given, F of C, and then we have a unit vector, direction vector from U, A to C. So all we really need to find in this case is just that unit vector. Okay, so first thing is we're going to find this position vector from A to C. So what do? Well, we look at it and say 2I, so that's how far along the X. 3J, that's how far along the Y. And minus 6K, which is, so here's our position here, and we're going down. So this is like our, this is not really our origin. Our origin is basically like here. So we're going down by 6 meters. So we write it out. Here's our position vector, R, A to C. Okay, and we can find the magnitude, and then we just use our formula essentially, which is just, you know, the vector RAC divided by its magnitude. Okay, so a couple of steps. What we recognize is that this force vector is in the same direction, so UAC is both the direction vector for the cable and for the force, okay, because it's acting along the cable. All right. So we just go ahead and do the math, and this is our final result in Cartesian coordinate system, right? So here's another problem. Okay, so two forces acting on a flagpole, and we have their magnitudes, and we're um, we're given their positions essentially. Okay, so same thing as before, as we previously did, except now, oh, so we want to find the resultant force and its direction and coordinate direction and direction angles. Okay, so just find the forces along those A, B, and AC. Okay, so we're going to find those vectors and then add the forces to get the resultant force. So we're getting the vectors for the vectors for these, and we're going to add the individual components, and then we're going to go ahead and use that to find our coordinate angles or direction cosines, let's say, for that final one. Okay, so here's our AB, RAC, just as before, making this like our origin, how far down it goes. That's the -6, so they're both the same for that. And then along each of the axes. So the B, A to B is this one. So we go 2 in the x direction, and then 3 in the y direction. Okay. Oh, sorry, -3 in the y direction. Okay. Going from there back. Right. And then the other one is, 3 in the x direction and 2 in the positive y direction. Okay. So we just follow the same process, use Pythagorean theorem, and we come up with our vectors, the magnitudes, and then we just write it out. Here's my RAB, okay, and the same thing, my RAC. Perform the math, and you have the two vectors. Okay, so here's our two vectors, FAB, FAC, and we continue along. We add the individual components together for these, and here's my result after you add the individual components. Then you use that Pythagorean theorem, find the magnitude of that vector, and it comes out to be 1175 newtons. And then you just use that to find our direction cosines, or our angles. Sorry, here's the direction cosines, so that we find the angles. Okay, so that's it for this part. Cover 2.9 in the next one.